use the right one. Okay, working with the 5.4, working with integrals. First part, integrating even odd functions. Even odd function properties can be found as a quick review in chapter 1 about the function reviews. Look at the last section for the property of the functions. Even odd function, the symmetry with respect to the x-axis, y-axis, origin, something like that. And then the last part of this section is about the average value of the function. The following part of it, I would consider these two as the combined as the same concept, mean value theorem for the integrals. The first one, integrating even and odd function. Quick review. For an odd function, you can identify the function as an odd or even by checking the function at negative x. If the function at negative x turns out to be negative of the function, or it comes out as the opposite inside of the original one, this function is an odd function. And the symmetry of this is about the origin. For the graphical way, the quick way to recall this property is if portion shows on the first quadrant, the reflection of it will be in the third quadrant, or if reflected to the opposite quadrant. For example, y equals x to the third power, which is the cubic graph. As you see the symmetry, you have the portion in the first quadrant. When you reflect it, it will go over to the third quadrant. And also y equals sine x is another example of the odd function. So the portion here is reflected over. We call it symmetry with respect to the origin. And in the informal way, portion in the first quadrant is symmetrical with the portion in the third quadrant. Okay, this portion, this portion. So these two are quick examples, the quick reviews for you to recall the odd function examples. For the even function, you test the same way as when you test with the odd function. If you replace x with a negative x, the function comes out to be exactly the same as the original one. And this case, the graph has symmetry about the y-axis, or it's flipped from the left to the right. This example, the quick one, y equals x squared, or the parabola graph. Okay, as a parabola, you can see the right portion reflect about the y-axis to have exactly the same as the portion on the left. Think about the order pair. For the order pair, back to the odd function. If this is the order pair, like you have x comma y here, both of them are positive, and it reflected with the point here, which is negative x, negative y. That means you replace x with the opposite, it comes out as the opposite of the y. Okay, from order pair xy reflect to negative x, negative y. For the even function, I use the graph that easy to manage here. If we have x comma y on the right hand side, it reflected to the left side. So that means x will be opposite, but y is still positive. That is similar to the way that you analyze it or verify with the function notation. You replace x with the negative x, but the y is still the same value. So it goes just from the right to the left or the left to the right, where the odd function will go to the opposite quadrant. Okay, and the example of the graph that I put over here, for the graph of the odd function, if you pick the order pair on the second quadrant, the x is negative, the y is positive. It's reflected to the opposite quadrant, that is quadrant number 4. The order pair will become positive for the x, but y negative. So kind of both of them will be in the opposite inside. Okay, how do we use this property for the integration? If you find the integration to find the area, just for this property, as you see, the definite integral from negative a to positive a. Lower limit, upper limit, they are opposite. So that means it's away from the 0 point with the same quantity to the left and to the right. Okay. Similar to the odd part, if you are going to find the definite integral from negative a to positive a of the function with respect to x, for the odd function, the graph is symmetrical with respect to the origin. So from negative a to positive a, you have equal area, but one negative, one positive. So then the definite integral, which represent the net area for the odd function will be 0. For the even function, the graph, like for example, the parabola graph, from point negative a to positive a, they are exactly the same and y still the same value. So instead of finding from negative a to a, you can cut back the calculation to be like twice of the definite integral from halfway to the right end or from the positive side of the function with respect to x. So instead of finding the value from negative a to a, you just find a half and multiply by 2. The even function, the definite integral from negative a to a is not 0. But for the odd, it will be 0 because the definite integral is the net area. Portion of it is negative, the other portion is positive. So positive, negative, they adjust each other to be 0. So this is the use of the even and odd functions when you find a definite integral from point negative a to a. Okay. Now, for the example, this example asks you to use symmetry to evaluate the following integrals. Another way we check whether the function is odd or even. Okay, odd or even. For the odd, we call the negative from negative a to positive a of the odd function gonna be 0. Negative a to a of the even function is gonna be twice from 0 to a of the even function. We have to do for this kind of problem is to identify our function for number 1 is x to the fifth. Ask yourself, is that odd or even? If you are not sure, use the graph and you should see the portion on the right on the left, either it's reflecting from the right side of the graph to the left side of the graph, or it's reflecting to the opposite quadrant. For the polynomial function, the power is used to identify whether it's odd or even. The 5 is an odd, similar to x or x to the third. I use the example x to the third as an odd function. So this is similar case. And another observation from negative 100 to 100. So then we can use this kind of the property. Otherwise, we have to go back to the traditional way to find the antiderivative and evaluate at the lower limit, upper limit. Okay, for our problem, since x to the fifth is an odd, you do not need to do anything. As long as you can verify this as an odd function, the integral gonna be 0. That's it. You use the symmetry to evaluate. You're done. You do not have to find the antiderivative and get the value out. So cut back your process of getting the solution or your step of getting solution. Okay. So that's the number 1. Use the symmetry. Next one, number 2 here, we have negative a to a as a equals 5. Okay, away from the 0 to the left 5 units, to the right 5 units. And the function we are working on, f of x is 10x to the fourth minus 2. Look at one at a time. The coefficient is okay. We just consider the power. For the power 4, see the x to the fourth here, the power 4, that is an even number. The first part is an even. Check the second part is at an even function. The quick way, if you have the constant means multiply by x to the power 0, is also an even function. Both of them even. If you are not sure or you don't want to use this way, another way to check is replacing x with a negative x. See what comes out. This is a concrete way to verify. Replace x with a negative x, it comes out negative 4 to the fourth, becomes positive x to the fourth. So 10x to the fourth, nothing to do with the 2. It returns exactly the same as a function value. So this way, it totally clear that the function f of x is an even function. For the even function, what we have to do as we evaluate from negative 5 to positive 5, this one can be broken into two pieces equally. So we're going to find it as twice of the definite integral from 0, which is the midway, because 0 is in the middle of negative 5 and positive 5. You just find a half and multiply by 2. So evaluate from 0 to 5 of 10x to the fourth minus 2 with respect to x. This time for the even function is not 0. So you have to work on it, but just make it less complicated when you work on the algebra part. So we have 10x to the fourth minus 2. Antiderivative is 10 multiplied by x to the fifth over 5 minus 2 means the antiderivative of 2 is 2x. Okay, and then evaluate from the variable x 0 to variable x 5. Simplify the number 5 and 10, reduce to be 2. We have too many tools here, make it easier to calculate. So I'm going to factor the 2 from these two terms out to join with the 2 out front, becomes 4 times x to the fifth minus x. We're not going to factor x because we're going to need x to replace with the number. And then evaluate from x0 to x equals 5, 4 as the coefficient, and then multiply by the first group from using the upper limit 5. So 5 to the fifth minus 5, subtracted by 0 to the fifth minus 0. And the number will come out as, let's see, it's going to be the last number. Yeah, it's very last number. It's 12480, I believe. It's 12480. Okay, so this is the use of an even function property.